Today we have two of our OE grad students presenting. They're going to be at a conference next week in Halifax. They thought they'd present some of their findings to us as practice and also so we can know what's going on with them. We have first up Hannah Arnholt with a focus on bio-inspired underwater perception for uncrewed underwater vehicles. Hannah Arnholt is a Ph.D. student at the University of New Hampshire in ocean engineering. Hannah received her Bachelor of Science in Mechanical Engineering in 2017 from the University of Miami, working on combustion engine intake efficiency for her senior capstone project. After completing her undergraduate degree, Hannah worked as a software systems engineer for Raytheon Technologies in Mass, before deciding to return to school for her Ph.D. Aside from her Ph.D. research, Hannah has also been a graduate advisor for the Marine and Naval Technological Advancements for Robotic Autonomy, the MANRAG, since 2020, which consists of not only aiding with developing different marine robotic platforms, but mentoring the different students to help with the project. Hannah's PhD degree is currently being funded by the DoD Smart Scholar Program. Is it DOD?
No, DoD.
DoD, okay. And she'll be working at Naval Undersea Warfare Center in Keyport upon completion of her degree. We also have Maggie Enderle, Margaret Enderle is a master's student at the University of New Hampshire in ocean engineering. After completing her bachelor's degree at UNH with a senior capstone project developing propulsion of robotic fish, she has continued to build on that research in her graduate program. Her current work focuses on pitch control of robotic fish using pectoral fins, which is the work she'll be presenting today and at Ocean's Halifax conference next week. Welcome, our speakers.
Well, thank you, Adriano, for the introduction. And a lot of you already know me as one of your seminar coordinators, so I'm happy that you can finally see what my research is. And today I'll be presenting just that. The name of my overall dissertation research is the Marine and Naval Technologies for Integrated Sensing, or MANTIS, which is this bio-inspired perception. And as Adriano mentioned, it's sponsored, my studies are sponsored by the DoD Smart Scholarship Program, and then my actual research is funded by the Office of Naval Research's Naval Undersea Research Program. So my outline for today, the first half is going to actually be what I'll be presenting at the MTS IEEE OCEANS conference next week in Halifax. And then the second half is a little bonus content since our time limit for that's 12 minutes. So I'm going to give you guys a little bit of a treat where you get to see my current research, what I did out in Keyport, Washington this summer. Part of the DoD SMART program is you have a internship requirement. So that's what I did this past June through August out in Keyport, Washington. So I'll give you guys a little peek into that world. So diving right into my research that I'm going to be presenting next week at Halifax. The title of the paper I'm presenting on is using ambient sensor data to characterize and predict autonomous perception sensor performance. And my co-author on the paper is Dr. Maywin Thane, also from UNH. A lot of you might already know her, and she's also one of the advisors of the Manta Ray group. So this is an outline of the presentation. Pretty standard, and we'll just dive right into it. So we'll begin this talk with a really big ask, and it's how can we make these low-cost micro uncrewed underwater vehicles, or UUVs, more efficient? And especially knowing we have higher cost UUVs already available on the market. Why are we looking into these lower cost ones? Well, one reason would be a PhD student like myself who's relying on limited research funds. I couldn't go and afford one of these higher cost UUVs. Another reason, if you want to create some sort of swarming situation where you have a lot of UUVs, getting a lot of lower cost vehicles is a lot more efficient than funneling all your money into one higher cost one. But the trade-off for these lower cost vehicles is how well they actually work compared to their higher cost counterparts. And we're not going to see the same performance in our lower cost vehicles that you do in the higher cost ones. But how do we accommodate for these trade-offs? Well, we make an algorithm to take what we have and what we're working with, predict how it's going to perform, and then work around this information to optimize emissions. And this is where we came up with the Standardized Heuristic Algorithm for Reinforced Calculations, or SHARC. So SHARC is a three-phase algorithm where first you consider what sensors you have on board, what you're working with. then predict what the performance of these sensors look like, weighted on the ambient information that's around the sensor package itself. And then you're going to leverage this information to optimize your vehicle perception performance. In the case of this presentation, we're focusing on a mechanically scanning imaging sonar, and that's going to be our perception sensor. And for our ambient sensor, we're going to use conductivity, temperature, depth, or a CTD sensor. Then we're going to predict and model the performance of this perception package to improve our vehicle mission performance. Now, to begin using SHARC for our sonar, we need to break down and identify what we need to determine for our performance metrics. In this case, we're going to look at our signal-to-noise ratio, or SNR, since that'll lead us to our probability of detection for our source itself. So we have this sonar equation here, which is how we're going to determine this SNR, and which will lead us to our probability of detection later on. And to use this equation, we need to identify 4 variables here: our source level, our transmission losses, our target strength, and our detected noise levels. Here we're going to start with our source level, which for this study, like I said before, we're looking at a mechanically scanning imaging sonar. The sonar we used was Blue Robotics Ping 360, and the reason we chose it was because it's easily available on the market and it has a lot of similar counterparts, so that we could also test this algorithm with. The sonar itself has a central frequency of 750 kilohertz. We assume the far field approximation and that the transducer is a line array. So we found that our source level would be about 235 decibels, referenced to a pressure of 1 megapascal. The next thing we're going to look at is our target strength. So we're going to go a little bit out of order. And while you're in the marine environment, you consider a target such as vegetation, sunken structure, fish. In the case of this research, we're going to look at a men's regulation water polo ball. And yeah, a polo ball you don't really find in the wild too often, but I chose this target because it's easily accessible and it also makes things a lot simpler to model since it's an air-filled sphere. So using URIC's target strength calculation for a perfect sphere, we find that that target strength is about 24 decibels. So now we have our source level, we have our target strength. Let's look at the noise around both of those things, and we're going to use this equation to find our detective noise level. The first variable I'm going to focus on here is our noise level itself. Since we're using such a high frequency source, we're going to assume that it's self-thermal noise limited, and using Harlan et al.'s equation here for noise level, and using frequency in kilohertz, we can determine that variable. And the other 2 variables here are also dependent on the source, where you're looking at your bandwidth and directivity. And that gets us our detected noise level. And all that leaves us with is our transmission losses, which is a lot trickier to solve, since there's a lot more variables involved with that, and that's kind of where our simulation comes in. So we used the BELLHOP simulation from Michael B. Porter to determine these losses. The simulation itself determines beam pressure throughout a discretized simulation frame throughout a pre-specified channel to solve for our transmission losses. And when you get that, you can get a nice image like this, where that point over there is where your source is, and you can get the transmission losses throughout the range and depth of your source. To initialize all of this, we have an environmental file we can fill out where we can specify our sonar characteristics such as central frequency and beam height, our water column characteristics such as sound velocity profile, bottom acoustic characteristics, and channel range or length and depth. And we can also specify where we want to place our source or sources, and number of calculation points as denoted by RD or NRD across length and depth. Because we can also specify our sound velocity profile, or SVP, this is where our CTD data comes in. And we pulled from several historic CTD data sets from all across the North American region. One right from the Gulf of Maine, another from the Hood Canal out in Washington, and a third extrapolated from the Beaufort Sea. We also have a control group of 1,500 meters per second throughout the depth of the profile. And then we plug this data into an approximation of Del Grosso sound speed equation to solve for that sound speed value. So going back to our sonar equation, why do we need this again? Well, it's to get this value here, which is our probability of detection. The last variable to identify is our false alarm rate, which we're going to assume to be 10 to the negative fourth based on Ainsley's sonar performance modeling text, and we can solve for that probability of detection. But since we're going to have such a wide range of values based on how many solving points we put in our simulation, we came up with an averaging scheme where for every source depth specified within our simulation, PD across our beams are averaged by evenly distributed steps away from our source, filtering out values outside the beam. And then averaging was done across groups of beams for each source sample. We were then able to use these averages to gauge the general range performance for different PDs away from the source. This takes us right into our results here. The first thing we noticed upon running BELLHOP was that there are reflections imposed upon the bottom and surfaces within the simulation. And while normally, especially for a study like this, where we're looking at environmental effects, this is kind of ideal because we want to assess those. We found that things were looking a little too even throughout all the runs. While this is the control group, I was seeing similar patterns throughout all of the CTD profiles. And we could not figure out a solution to actually filter that out, whether it was to completely eliminate those boundaries. So for the shallower water column runs, such as less than 10 meters, we weren't able to really reduce these effects. So we focused on these deeper 45 to 50 meter channels to kind of get out that, and focused away from those boundaries to make sure those weren't interfering with our results. Now with that information, we took that snapshot of the column 5 meters from each boundary and focused on the range band where we see a probability of detection of 80% or PD equals 0.8. These results were extrapolating using the averaging technique I specified in the previous slide, and each range represents range away from the source, and each depth is the depth a source was placed throughout the simulation. PD 0.8 was chosen because it was desired for sensor performance, as well as the last performance band prior to seeing those effects I described previously. And what we notice here is that for every sound speed profile, we're starting to see variances forming within the different depths. And to further break this down, we plotted each 0.8 average depth band along with the line fits of the different parts of the SVPs, which I'll go over in the next few slides, starting with the Beaufort Sea. The SVP here was a little more linear. There was only about 1 meter per second change throughout the 40 meters shown here. And the change of the linear fit was for the different directionalities, but we start to see that as less change occurs in the SVP, the further out we can achieve that performance that we want to see. So you have more room to actually see that performance. Whereas when there's more change, you get less space, which we can see in our more variant SVPs, such as the Gulf of Maine, where you have more change at the top of the SVP due to change in temperature from this profile. And you can see that at the top there, where there's more change, you have less range to get that desired probability of detection. But as you travel deeper into the water and the SVP becomes straighter, you get more of a pushed out range to actually get that desired probability of detection. And finally, we see that with our last SVP from the Hood Canal, where this one was changing due to a change in temperature and salinity, and we're still seeing those effects where towards the top of the profile where there's more change, you get less room to get your desired probability of detection. As you get deeper down, you get more range of your desired probability of detection. And plotting these observations for the line fit slope of the SVP curve against the average maximum range, we can see there's a positive correlation between the two. So as you get more slope in the SVP, we get more range of our desired performance. Less slope, less range of that performance. So how can we use this with SHARC permission planning? Now that we know about that correlation on the previous slide, if we have a pre-captured SVP prior to our UUV deployment, we can plan around our deployment depths and patterns based on how far out that desired range is. So say you're using a pattern where the UUV is traveling back and forth like someone mowing a lawn, you can increase or reduce those passes depending on how much you can predict your range will be for your desired probability of detection. For our experimental testing, which you guys will get a sneak peek, we plan to implement this in different ocean environments, where that's why we chose a target like the water polo ball and an easily accessible sonar like the Ping 360. And some of this testing already began in Washington State this past summer using the Ping 360 and the water polo ball, and all of that work is currently ongoing. Finally, we'd like to apply SHARC to different sensor types such as stereo cameras. And while the studies focus on the acoustics portion, we believe SHARC could be applied to the different perception sensor systems on board these low-cost UUVs. These are my acknowledgements for the paper itself, as well as my references. So then this is going to bring me right into my current research, which I alluded to. But before we get into that, I just wanted to introduce the manta ray group for those who don't know a lot about it. Dr. Maywin Thane is in charge of it, along with our co-PI, Dr. Yuri Ruzhinov, who actually sits up in CCOM. And the manta ray group partners with the Advanced Control Lab, one of Professor Thane's other labs on campus, focusing on quadcopters. And the main mission is to connect all of these different systems between undersea, surface, ground, and air to create a collaborative environment of all of these uncrewed vehicles. And I think Professor Thane's in the room, but her pipe dream is for friendly Skynet, which I always laugh at. But that's the overall goal of the collaborative ecosystem that she's in charge of. And then I just wanted to give you guys an idea of what our day-to-day looks like. As Adriana mentioned, I assist with the platform designs with the undergraduates, as well as I'm a mentor for them. So we go on trips out to Keyport, which was actually from the summer. We work on vehicles together. Our undergraduates always present at the URC at the end of the year. And our grad students, we try to go to the Jere or the SOE graduate symposium, and so on. So the objectives of my research is defining this bio-inspired set of techniques for autonomous perception using a multidimensional approach, and using these multiple sensors and multiple perspectives. And what I mean by multiple perspectives is we have multiple underwater vehicles capturing different viewpoints, or you have one underwater vehicle capturing a bunch of viewpoints and we place it all together. We're developing this for missions such as detecting underwater unexploded ordnances, or UXO, or even observing confined aquaculture pens. For those who saw Dave's presentation last week, we've done some collaboration with Aquaport, and Maggie's research kind of centers around that. And we're kind of trying to make these techniques generalized to ensure modularity. So going back to that low-cost UUV question, how can we make this as low-cost and modular as possible to put on all of these different platform types? Going back to the spring before I went out to Keyport, I got kind of a mantis in a bottle, or in this case, mantis out of a bottle, where I hooked up a Raspberry Pi to the Ping 360 sonar, along with a temperature and depth sensor. And I got things working with Blue Robotics has a Linux kernel that I was able to install onto the Raspberry Pi and access through the tether to my top side, which was a Windows 11 laptop. And you're able to SSH into the Pi, do diagnostics as your sensors are running. At Keyport itself this summer, I switched from Windows 11 to Ubuntu 22. Things still ran the same. Ubuntu, for those who don't know, is a Linux system as well. And this is the actual mantis in a bottle now. At Keyport, they have an innovation center where I was able to 3D print an electronics tray to organize the bottle itself. And the one thing I'd like to note is, due to some shipment issues, we did not have a conductivity sensor for the summer. So the results that we got were only for temperature and depth for our CTD package. But based on historic data from Keyport, that time of year, we weren't expecting much change for salinity anyways. But going forward, we're gonna work on getting that conductivity sensor. And then this is just a snapshot of the actual package working on the Ubuntu machine, as well as Keyport helped me create my own logo for my research and laser etch it on the bottle end cap. So that was pretty fun. Along with sonar testing, especially in an area that has a lot of marine animals and you have a military facility, so a lot of the waterways are controlled. There's a lot of environmental considerations. So I got to meet a lot of pinnipeds this summer, looking at different test sites, as well as filling out different environmental review board paperworks to make sure that my non-de minimis source was not going to hurt our pinniped friends. I had 2 successful deployments, and it was aided by other UNH students out there this summer for internships, as well as some UNH alumni who are working out at Keyport. This is us doing our deployments. And my next steps for that is to process that data. I saw if I had a chance to do that since I got home, and then repeat the same tests at our facilities here at UNH. Aside from the sonar, I also mentioned that following studies would be with stereo cameras, which we've also started looking into. We've acquired 2 Z stereo cameras, and we're going to test those in the labs for different ambient light levels and see how the performance of those cameras change. And same thing, we're going to test that in the water, hopefully at the UNH facilities over the next year, and maybe even out in Washington again this summer. This is some information about the SMART Scholarship. If any of you guys are interested, you're welcome to reach out to me. And this is some information about the Naval Undersea Research Program that actually sponsors the hardware components of this research. These are my acknowledgements. I'd like to point out the Keyport Innovation Center because they kind of housed me this summer at Keyport and printed things. And otherwise, everyone on this acknowledgements has been a huge help for this project. And I'd like to open it up for questions.
The Mantis housing, is that from the robotics too, off the shelf? Have you noticed any issues with leaking with that in your deployments?
No, so I vacuum test before deploying, and I have not personally had any issues. I usually put a desiccant in as well, and I have a leak sensor running. So actually when I'm running it, and because I can maintain that SSH connection, I have a program that's going to say SOS leak if it does leak, but I haven't had an issue with that quite yet.
Okay, that's good. We had that issues.
If you have questions or comments, it's better than those mean Canadians next week. Anyone has anything? No? All right, thank you, Hannah.
Oh, Jenna?
What method are you using to submerge a men's regulation water polo ball underwater and at what, like how are you varying the depths on that?
Great question. I don't know if I have a picture of it. Yeah, so if you look right here behind me, I actually have an agricultural like equine hay feeding net that I got to put the actual polo ball in. So I'm hoping those ropes, because I haven't gone through the data yet, I don't know how those ropes are going to interfere with the sonar itself because it's such a high frequency, it'll probably pick up. But I have it in the net, and then I tie it all up and put a bunch of weights at the bottom of it. So that's kind of how I got it in the water, and then sunk it off a pole.
Can you do those tests in the tank here? Like in our calibration facility, could you like, if you
Yeah.
needed to, do you have to do them in the ocean or can you do them here?
No, I could probably do them here. And actually that would probably be a good environment to look at the different reflections and how they can interfere. I did start dabbling with using BELLHOP with some of the parameters from the engineering tank to kind of try to simulate that beforehand too. But that's something that we've kind of looked into and also talked about doing.
I have a question. I'm not sure I understood what you meant by when you're using the BELLHOP equations for the modeling. It's the top interface that was giving you problems?
It was the top and the bottom. So if you look,
That'd be the seafloor and
Yeah,
air
so-
water interface?
the nice thing about BELLHOP is you can actually specify what your boundaries are. So if it's a pressure release boundary or just a rigid boundary. And then also you can specify what the different sound speeds are, the absorption coefficients, depending on the boundary type. So here we have just a normal rigid boundary at the bottom. I used characteristics for a kind of sandy bottom, and then the top's just a pressure release based on the surface. And we got this kind of banding where you can kind of see it going like that and it looked identical kind of for all of the runs we were doing. So it was coming off of both boundaries.
It's
And
like an increase.
yeah. Yeah, it was an interesting effect, and that's why I'd like to do experimental to see if we get any similar results. And I know there's some work in the building also looking at those different bottom characteristics and how they appear.
Could be some scattering.
Yeah. And again, because it's such a high frequency sonar, that's something we'd expect. We just kind of tried to simplify everything for this paper. And because my dissertation research isn't directly looking at acoustics, we tried to generalize as much, but it would be interesting to collaborate with acousticians to look further into those effects.
All right, well, thank you, Hannah.
So as Adriana said, I'm Margaret Enderle. Most of you know me as Maggie. I also go by Margot, whatever you want to call me. Hi, I do work on robotic fish, and so my talk today is going to be about my paper for Halifax, but then I am going to go a little bit into the history of the robotic fish here at UNH, and some of my work on what I hope to do in the future through my research using the robotic fish. So my paper today is titled Mathematical Model of Subcarangiform Robotic Fish. I do this work in collaboration with Dr. Maywin Thane through the Marine and Naval Technological Advancements for Robotic Autonomy Group. The vehicle I specifically work on is the GHOST Uncrewed Performance Platform Submersible, or GUPS. GUPS is designed to be deployed in an unobtrusive environmental monitoring conditions. At UNH here, we deploy it in the aquafort, or the aquaculture setting off of Newcastle, New Hampshire, to observe wildlife and environmental conditions without disturbing the natural wild marine life. At the beginning of this work, GUPS was able to swim in a lateral 2D plane using subcarangiform motion with a servo mounted at the back of the body and a driving location at the third tail linkage. This work splits the robotic fish into 4 linkages as shown here to help simplify the calculations. In addition to the subcarangiform propulsion, pectoral fins were implemented on the robotic fish. These pectoral fins were added to have an airfoil cross-section in order to have known drag and lift coefficients for simplification. Unlike reef fish, who swim in all different directions in coastal environments, trout, carp, and other fish of similar class that this is based on, that our specific robotic fish is based on, maintain small pitch angle behavior. Koga et al. Helped quantify this as a maximum pitch angle of 35 degrees. So that is what we will be using in this work as the criterion to try and stay below in our case studies. So getting into the mathematical modeling of the subcarangiform propulsion, Koga et al. Has this equation where we look at all of the different couplings between each tail linkage and the external forcing. External forcing are calculated as such, where T is our input from the servo motor, and it is kept constant through all of our different cases. Forces are calculated here, which gives us ultimately an angle between each tail linkage and an overall angle of the caudal fin, or the rear fin of the fish, in relation to the center line, and as well as the overall thrust force that is produced. Going into pectoral fins, Zhang et al. Gives us these equations in 3 degrees of freedom, where the delta P is the servo input from the motors that are in the head of the robotic fish, which is what we will be varying in this study. The drag and lift forces are calculated here, where the drag and lift coefficients are known based on the airfoil dynamics, and the velocities are calculated as such, giving us our surge, heave, and pitch forcing in these three directions. From Fawcett, we get to this equation where we have the moments of inertia, the Coriolis effects, drag forcing, which is estimated using SolidWorks flow simulations, which gives and the previous slides give us this forcing vector tau. This culminates into a mathematical model, which is calculated using MATLAB Simulink, and this model in 5 degrees of freedom is used to produce all of the figures for this work. It was decided to use sinusoidal pectoral fin inputs to investigate the pitch dynamics of the robotic fish. So the first 3 cases are a fairly low frequency oscillation, whereas the final case study gets into high frequency oscillations. Case 1 was almost the extreme of the simulation before the system became unstable, where we are using a 25-degree amplitude and 80-second period oscillation for the pectoral fins. With the larger period of the waveform, the robotic fish had more propulsion with higher pectoral fin angles, which increased the overall pitch angle of the robotic fish. This produced higher than 35-degree outputs, as seen in this bottom left figure here. As it is also seen that there is a system delay between the pectoral fin input and the system response of approximately 13.7 seconds. In order to narrow in on this 35-degree threshold, case 2 decreased the amplitude and period of the input, having a 20-degree amplitude and 40-second period. This did in fact decrease the pitch angle of the robotic fish, but it still has a pitch angle of over 40 degrees. It is also noted that there is a vertical drift in the output forcing response for the robotic fish, and this is assumed to be based on errors in drag coefficients, especially in the vertical direction. And so we will be assuming that the first period of oscillation of the response was constant through all of the simulations. Another interesting point we found with this study was there is a vertical asymmetry between the positive and negative inflection points of the input, which is concluded to be geometry based. This could lead to further exploration of these geometry based implications. Case 3 further narrows in on our 35-degree threshold with a 10-degree amplitude and 20-second period. And this does in fact satisfy the 25-degree or 35-degree pitch criterion that we are looking for. And so this is determined to be our maximum operating condition for inputs for the pectoral fins. Case 4 switches gears a little bit and looks at more high frequency inputs of pectoral fins with much smaller amplitudes. This case uses a 5-degree amplitude and 2-second period for the input, and understandably there is not as high of a frequency in the response oscillations. With the larger system, the robotic fish does not have the ability to oscillate at the higher frequencies, and so the input frequency of the pectoral fins is found to be very closely related to the frequency of the caudal fin or the tail fin oscillation that is given. Further research is to be pursued about the relationship between these two oscillation frequencies and how that affects the dynamics of the robotic fish in overall. In conclusion, we've found that there are larger pitch angles that occur when there are longer period waves of input, and the geometry-based sinusoidal asymmetry was found in our response. Additionally, the maximum operating condition was determined with a 10-degree amplitude and 20-second period for the robotic fish, and that will be used going forward to attain that biomimicry. Finally, the output frequency of the response oscillations was found to be closely coupled with between the tail oscillations and the pectoral fin oscillations, and that is going to lead to future developments down the line. Going forward, I would like to experimentally verify these results using the robotic fish. This is our robotic fish in the engineering tank earlier this summer. And with the enhanced understanding of the pitch dynamics from this work, I hope to implement a pitch control algorithm to help control the UUV. Additionally, we have added some fins, and I hope to look at the effect of these fins, especially the dorsal, so the dorsal, anal, and pelvic fins, and see how they affect the dynamics of the robotic fish overall. A special shout out to all of these lovely people and groups who have supported me in this research and helped me get to where I am today. Here's a list of references. I'm going to hold questions for a moment as I go through a bit of the history of the robotic fish as it started 4 years ago plus, and see how far it's come to today. So we have PVC gups is where this kind of started. It was a COVID project of Hannah's, and it was made using PVC pipes from an online Instructables project. This has 2 servos in the tail, but it only had a tail. From 2020 to 2022, some senior project design teams helped develop this robotic fish to become what we call skeleton gups. So this has be able to become and achieve the quintessential flap motion of the robotic fish in air, but as you can see here, the tail does not displace all that much water, and so did not produce sufficient propulsion underwater. That comes to 2022, 2023. This is where I came into the project, and through the senior capstone team that year, the surface area of the tail was increased, which was able to produce sufficient propulsion for the URC. So we painted it all up to look like a steelhead trout at the URC. And one thing to note is we won the URC competition in the ocean engineering section that year. But it was pretty cool. Some of you were there and saw our robotic fish in the water, but that's something I'm very proud of. This past year, between 2023-2024 academic year, the pectoral fins were added, and as well as some of the other fins. Of note, the 2022 to 2023 group was much larger than the group this following year. And so the addition of the pectoral fins was a smaller step. However, there were understandably fewer people. In addition to the addition of pectoral fins, we had a group of biologists start working with the aquafort and looking at the behavioral impact on the fish between having a robotic fish in an unobtrusive environmental observation capacity, looking at and seeing how the fish reacted. I don't know, I thought I set this to loop, but they put a couple of different varieties of robotic fish painted up in different colorings. So this is the steelhead trout coloring, and so it's trying to blend in. They had one that was a spiny dogfish, so a natural predator, and then the third was just a plain black, no coloring. And determining whether or not the fish reacted differently to the different colorings, or if they reacted at all. And found that in this aquaculture setting, where the aquaculture raised fish in very close relation to humans, and like the boats go out there twice a day, plus to give them food, they found that in an aquaculture setting, the fish don't care. And so with this, GUPS is almost looking for a new purpose. But I am curious of how would natural fish in the wild react to this robotic fish versus another underwater vehicle in more of your standard capacity? And would natural wild fish have more of an effect with this robotic fish? And so, if anybody has any ideas, we're open. But coming to the present day and where we were at the end of the summer 2021, we have added some of the fins that have been discussed already. And in the transition from the URC winning Denise to Dennis, they switched from a Arduino to a Raspberry Pi, which had many struggles of its own, but allowed both the simultaneous operation of the caudal fin tail and the pectoral fins, and also allowed us to add a tether. Through the past academic year, the fish had not been able to swim, and so Dennis finally splashed down in August, and we are very proud of him. But with the addition of the dorsal fins and pelvic fins, which have spines in them to be able to be actuated in the future, it makes it very top heavy. And so Dennis has a life jacket, which is kind of ironic that our robotic fish has a life jacket. So that is one of the first things that the new senior project team is going to embark on, is figuring out the ballasting of the robotic fish. But here's also a video with our fins, and it looks kind of cool. Kind of looks like a fish up close. But with that, I would now like to invite questions for any part of my presentation.
So I know that designing a functional swim bladder is like the hardest part of any robotic fish. And ballasting, like you said, requires a whole senior capstone team of their own. Does your model for the changing pitch angle, does that neglect the effects of buoyancy changes and like act under the assumption that there's a swim bladder that works and keeps it neutrally buoyant at all depths?
So one of the papers that I developed my model from does take into account that this various buoyancy considerations. And so it does have an active swim bladder, but the model that I'm using assumes a fairly constant or very minimal changes in buoyancy in the pitch that we are observing, and so it's being neglected.
I was curious about the mathematical modeling part of it. You mentioned there's a Coriolis term. Is that, I'm just, maybe this is just part of like the tool you're using, but is that, because it's like a scale where like Earth's rotation, I wouldn't think make much of a difference. I was wondering where that comes from. Is that like from the rotation of the tail itself or what?
It's based on a body-centric coordinate system versus an Earth-centric coordinate system. Once you go from a inertial frame to a body-centered inertial frame, you have to take into effect some of those Coriolis forces. Most of them are minuscule, and I believe in my paper we neglected them. But to get a full complete model, we just included them as in this paper.
If you put this fish in a moving stream and hold it still and disconnect the motors, do you get a similar type motion?
No. Short answer. But that would be really interesting to see. I don't think we've done any flow testing with it to get some of the drag coefficients that we did. The simulations that I've done, it did not behave that way, and so we looked at it in fairly static conditions. But the oscillation really comes from that servo motor in the tail, and so you don't get that natural undulation of the tail.
You said in your modeling you noticed that drift. Did that show up when you were actually testing or something that could explain it?
So that's something to investigate. Dennis just went in the water in August, and currently we're melting wires. So we have some issues to work out before I can do some real deep dives into whether or not that vertical drift is in fact real in simulation versus experimental, but I'm very curious to see if we'll experience that as well.
What was interesting is that change in frequency between the input signal and the output oscillations.
Yeah.
Which might be something scarier
Yeah.
if it's nonlinear or.
Yeah. Yeah. That's true.
In your results, there's like that funny cusping that occurs.
Yeah.
And what do you suppose is going on there? Is that like the fish stalling effectively, or the?
I think it is, from what we gathered, it was based on the geometry of the fish itself and how it comes over the top versus underneath, especially with the dorsal fin. And so that would be something to try looking at a carp versus a trout and seeing how that would change.
Can I interject a little bit? I can also say that this is a highly nonlinear system, and with a nonlinear system, as you actuate or change your actuations, you never know what you can expect from the output. So, as Maggie said, yeah, a lot more investigation.
So following up on that question, do they have damping systems with your controller to like keep it from going out of whack? If it's nonlinear and it starts to go, you have damping systems to keep it from.
So the system itself does not, and I did find in some simulations that it did go out of control, and that's why we kind of stuck to the 25-degree angles. If you give it very drastic angles in the pectoral fins, then the system does in fact become unstable. And so using some input limiting, we were able to kind of artificially do that, but the controller does not currently have any input, and so that would be something to investigate, especially as a pitch control algorithm is implemented.
Another question. I'm curious about how do I say this? Like how closely the physics, like the physics of how the robotic fish swims are directly analysis to the physics of like an actual fish, and like how much the separation of that analogy has evolved over the course of the project, like in terms of being more or less close to the exact sort of physics of how the actual fish swims.
Yeah, so especially with the subcarangiform propulsion, that is very directly related to how the fish actually swims. And a lot of those equations were taken directly from what was observed in, I believe it was carp instead of trout, but they took observations of the trout and were able to work backwards from there. But especially with the pectoral fins, for simplicity with drag and lift, I made them in airfoil, but with this version of the robotic fish, these guys are much more biomimetic. And so they actually have the fin rays, which introduce a whole other section of hydrodynamics. And so the math there does divert from the biomimicry there. And so the question is, do we go back down the path of, do we change the model to fit the bio, or do we look at a more controlled system that we know a bit more about, and where do we want to focus our energy?
Well, if anyone else has any questions, come talk to them after. I think we're over our time a little bit, but